Hi everyone, my name is Ruoyao Yang. Today I'm going to present DeepTest, automated testing of deep neural network-driven autonomous cars. My presentation is divided by 4 parts: introduction, approach, experiment results, and conclusion. First, introduction. The motivation of this paper. As advances in deep neural networks improves, it promotes the development of DN-driven autonomous cars. Also, in the world industry, autonomous car vehicles are being built and tested. However, there are some challenges in this world. Like traditional softwares, DNN often exhibits incorrect or unexpected corner case behaviors that can lead to potentially real-world fatal collisions. To deal with that, people devise some testing techniques. However, existing testing techniques depend heavily on manual collection of labeled test data under different driving conditions, which can become prohibitively expensive. Therefore, the authors of this paper design, implement, and evaluate DeepTest, a systematic testing tool for automatically detecting erroneous behaviors of DNN-driven vehicles that can potentially lead to fatal crashes. The second part is approach. There are 4 problems to address when developing an automated testing tool. The first problem is how to systematically explore the input and output spaces. Since the input and output space of an autonomous vehicle is too large for exhaustive exploration, so this paper devises a systematic way which uses neuron coverage to partition the input space into several equivalent classes and cover each by picking one sample. The assumption here is that DNN behaves similarly for inputs that have similar neuron coverage. Neuron coverage is computed by the number of activated neurons divided by the number of total neurons. An activated neuron is the neuron's output after scaling is greater than an DNN-wide threshold. This paper is 0.2. Similar to testing tools for traditional software, the DeepTest tries to generate inputs that maximize this neuron coverage of the test DNN. As experiment results shows, maximizing neuron coverage increases output diversity so that we can explore the input and output space well. For different models, we compute differently. For a fully connected layers, neuron output is directly output a single scalar value so that we can directly compare it against the threshold to compute the activated neurons. But for a convolutional layer, neurons output multi-dimensional feature maps so that we need to convert it into a scalar by taking the average. For RNN and LSTM, we unfold each hidden layer as this, and we take each enrolled unit as a separate one to compute the activated neurons. The second problem is how to synthesize realistic inputs to automate such exploration. This paper increases coverage by applying realistic image transformations onto the seed images and solving this problem. There are 9 different realistic image transformations and are divided into 3 groups. The first group is linear transformation. The first one is adjust brightness. The authors achieve this by adding or subtracting a constant parameter beta to each pixel's current value. The second is adjust contrast. It is achieved by multiplying each pixel's value by a constant parameter alpha. The second group is affine transformation. There are 4 types of this: translation, scale, shear, and rotation. Here is the example of each type of transformation. We achieve this by computing the dot product between the original pixel matrix with this transformation matrix here. The transformation matrix is 2 by 3 matrix, and here are the parameters used inside this matrix. The third group is convolutional transformation. The first type is blurring. We apply filters such as averaging, Gaussian, median, and bilateral, and compute and average the pixels with its neighbors. The second and third effects transformation are adding fog or rain effects by composing multiple layers from Adobe Photoshop on the input images to simulate realistic fog or rain effects. The third problem is, after we've defined the exploration process, how can we optimize it? As individual image transformations increase neuron coverage as proved by the experiment result, then we can ask the simple question whether they can be combined to further increase the neuron coverage. As also shown by experiment results, different image transformations tend to activate different neurons so that they can be combined to further increase coverage. However, since the state space of all possible combinations is too large to explore exhaustively, so that the authors use an alternative method, that is, a neuron coverage guided greedy search technique. It is defined by the pseudocode here. Firstly, we push all seed images into a stack, and GeneTest is a set that we store all the generated synthetic images. While there are still images to generate, while there are still seed images inside the stack, we pop one image. TQ is a transformation queue we use to record all the transformations we've applied and successfully increase neuron coverage. While the number of field tries is smaller than maximum field tries, we pop one transformation from our stored transformation queues. Or if there is no stored transformation, we just randomly pick one transformation from the whole transformation set. And then we randomly pick parameter for the transformation. For the second transformation are to be combined with the first transformation. We just random pick it from the whole transformation set. And we also randomly pick parameters for the second transformation. And then we apply the seed image, the two transformations and their parameters to generate a new image. Now we judge if the new image does increase the neuron coverage. We push all of our two transformations into our stored transformation queues and update the neuron coverage to the increased one. And then we generate and then we include the newly generated synthetic image into our all generated images. Or if the new image does not increase our neuron coverage, we just add number of field tries by 1. The main idea for this algorithm is to keep track of the transformation that successfully increase neuron coverage for a given image. That is why we firstly try to pop one transformation from our stored successful queue. Or if there's no, we just randomly pick one. And then we prioritize them while generating more synthetic images from the given image. The fourth problem is how to automatically create a task oracle that can detect erroneous behaviors without detailed manual specifications. The main challenge in autonomous cars is to specify the correct behavior of a self-driving car for every transformed image is almost impossible. So the authors propose an alternative way to define metamorphic relationships between the car's behaviors across different types of transformations. For example, the autonomous cars, steering angle should not change significantly for the same image under any lighting, weather conditions, or blurring or any affine transformations with small parameter values. Thus, if a DL model infers a steering angle θ0 for an input seed image I0, and it infers a steering angle θt for a new synthetic image IT, which the IT is generated by applying transformation T onto the original image I0. One can just define a simple metamorphic relationship where θ0 and θt, the two predicted steering angles, are identical. However, in real world, there are no single correct answers, so we can safely tolerate some small variations. There comes the trade-off on metamorphic relationships definition. If we define it very tight, there might be many false positives. That is, the model predict as erroneous, but they are actually safe. But if we define it relaxed, there might be many false negatives. That is, the model predicted as safe, but actually it is erroneous. Since this type false negatives might be more fatal, so we want to minimize it. And this is the formula to arrange this trade-off. A DL model predicts some output for the original image, and there might be a small but non-trivial number of errors. This is defined by this error here, mean squared error, MSE, and use this formula. Theta I is the true label for the original images, and theta OI is the predicted labels from the DL model using the original images. And since we want the false negatives to be smaller, so we want the predicted label from DNN to the synthetic images not differ much from the true label of the original images. So this is the true label for the original images, and this is the predicted label for the synthetic images after applying transformation T. And we want the square difference as smaller or equal to lambda multiplies this error. So the lambda is a configurable parameter that allows us to strike a balance between the false positives and false negatives. The third part is experiment results. Here are the implementation details. The authors evaluate their techniques on 3 DNN models that won top positions in the Udacity self-driving challenge. The first model involves 3 CNNs whose outputs are merged using a final layer, and it takes the differences among 3 consecutive images as input. The second model involves 1 CNN model for extracting features from the image and 1 LSTM model for predicting steering angle. The input of the CNN model is an image, and the input for the LSTM model is the concatenation of 100 features extracted by the CNN model from previous 100 consecutive images. And the third model involves only 1 CNN, and the authors use this dataset for training. This paper's experiments mainly investigate answers for the following research questions. The first question is, do different input and output pairs result in different neuron coverage? In the table here shows the relationship between neuron coverage and test output. Steering angle and steering direction are 2 model outputs. As we can see here, this column and this column, except for these 2 not significant. Almost all of the models neuron coverage are either positively or negatively correlated with the test output here. That means the neuron coverage is correlated with input and output diversity, so that given the same input to the model can generate different outputs, and thus it can be used to generate systematic test images. The second research question is, do different realistic image transformations activate different neurons? As we can see in this graph, this is the difference in neuron coverage caused by different image transformations. Given two transformations T1 and T2, the dissimilarities between activated neurons are measured by J-car distance here. N1 is the number of neurons activated by transformation 1 and N2 activated by transformation 2. As we can see, except from chauffeur LSTM, all the models has a high J-car distance. That means different image transformations activate different sets of neurons. As we can see in the figure here, this is the average cumulative neuron coverage per image. We first apply blur, then brightness, contrast, scale, etc. As we can see, the lines for all models goes up. That means all transformations contribute towards the overall neuron coverage. And also, we measure the percentage change in neural coverage per image transformation NT with regard to the seed image NO. The formula is here. As we can see from this table, all of the models, the numbers are statistically significant. So, which means the change is significant. And from this graph, we can see that different transformations thus trigger different sets of neurons, and they increase the neuron coverage at different rates. The third research question is, can neuron coverage be further increased by combining different image transformations? As you can see from this table, this is the cumulative transformation by adding all the effects of 7 transformations onto the original image. And here is the neuron coverage of the original image, and this is the guided algorithms applied to achieve the transformation. And we can see that the cumulative is already higher than the baseline, and the guided transformation is this much higher than the baseline and this much higher than the cumulative. Except for Rainbow S3, all of the models are significantly higher than the original. So that means systematically combining different image transformations, neuron coverage can be improved by around 100 with regard to the coverage achieved by the original seed images. The fourth research question is that, can we automatically detect erroneous behaviors using metamorphic relations? Previously, we defined this formula. The output that violates this formula are considered erroneous behaviors. However, for certain transformations, not all violations of the metamorphic relations can be considered buggy. We only report bugs for the transformations where the correct output should not deviate much from the labels of the corresponding seed images. That is, we check whether the MSE of the synthetic image is close to that of the original images. If it is close, then we consider, and it violates the metamorphic relation, and then we consider it as buggy. As we can see from the two tables here, the DeepTest has successfully detected more than 1,000 erroneous behaviors, and it predicts low false positives as indicated here. These numbers are really low compared to the synthetic images generated. And here are the examples of the synthetic images generated. And here are the false positives. You can see that the blue arrows are the correct labels, and the red arrows are the are the erroneous behaviors that might be fatal. As you can see, the red arrows always go to the wrong lines and may cause fatal collisions. And you can see here, this blue arrow and red arrow goes into the same line, so that it is false positives, but these cases are really few. The last question is, can retraining DNNs with synthetic images improve accuracy? As we can see in this table randomly selects 66% of either the original image or the synthetic images as the training set, and the rest of 34% as test set. And they uses the transformation with four transformations or ring transformations. As we can see that the retrained MSE is much lower than the original MSE as shown here. That's which indicates that retraining gives us better accuracy results. The final part is conclusion. Here is some related work with this paper. I've listed the main difference between this related work with DeepTest. The main difference is that DeepTest is testing image recognition and steering logic. It is a gray box mechanism that looks inside DNN to generate some synthetic images, and it utilizes metamorphic relations. It also specifically targeted at DNN, and it also more focused on realistic conditions. And finally, it defines new metamorphic relations and produces a continuous output. Here are some limitations regarding this, and we can try to address them in the future. Firstly, transformations applied by DeepTest are not designed to be exhaustive and therefore may not cover all realistic cases. Secondly, generated pictures may not be exactly reproducible in reality due to a large number of unpredictable factors, such as the position of the sun, the angle and size of the raindrops. However, as image processing techniques becomes more sophisticated, the generated pictures will get closer to reality. And third, DeepTest only tests the accuracy of the steering angle, but a complete DNN model for autonomous cars must also handle braking and acceleration. These two outputs can be addressed in the future. In conclusion, DeepTest is the first systematic and automated testing tool for DNN-driven autonomous vehicles. It tested 3 top-performing DNN models and found thousands of erroneous behaviors. The main contributions of it is it presents a systematic technique to automatically synthesize test cases that maximizes neuron coverage by applying different realistic transformations on a set of seed images. It uses domain-specific metamorphic relations to find erroneous behaviors of the DNN without detailed manual specification. And finally, synthetic images can be used for retraining and thus making DNNs more robust. That is all of my presentation. Thank you.